Hello. Today I'm going to introduce to all of you a perfect couple, and it's Zynq and HDL Coder. And let's start with why. And you have to ask this question to yourself before you do anything. So, why do we need Zynq? Because there are no other device such as Zynq with ace performance. The CPU can run up to 1 GHz and with the FPGA flexibility like Zynq. And also, Xilinx has done an amazing job on providing free resources like free RTOS or Linux. So we can build prototype fast and easy. And maybe we can bring our prototype to the production phase. And why do we need HDL coder? Because now it's all about timing. Let's say if you have a great idea, but this idea could not wait for 1 year to come to reality. So you have to use these tools to help you build your product faster. So you'll be able to put your product on the shelf, and people will, and there will be no competition, right? Because this is new, and also it's easy to use, and HDL coder is very easy and support Zynq interface. So that's why we need Zynq and HDL coder. And who will be benefit from this? Of course, obviously, the current Simulink users, and you don't have to worry about doing any extra things. You just implement your design by Simulink, and in the past you can only do the simulation, right? But now you can do more, like live demo for your algorithm. You can now you can bring your algorithm on FPGA and bring the FPGA to your customer or your coworker or your partner. And also marketing people could be benefit from this, because it's now you can differentiate your product by constantly like updating your hardware design, and which is the advantage of using FPGA. And the other is system or firmware or software engineer like me. And once you learn Simulink, which is very easy to learn, you can build a Cortex-A9 plus FPGA platform for high-end application without any RTL skill. So just imagine in the past, if I want to do something like this with FPGA, all I have to do is learn FPGA coding or learn RTL, either Verilog or VHDL. And now with the help of these tools, you don't have to, because you already have the idea and the concept of how to build a system, and the tool will do the rest for you. So the three categories list here could be benefit. So let's do this. So I've been working with Mathworks engineer to come up with this design. We use Simulink to create a Sobel edge detection algorithm, which is very common in any video application. And so we do the implementation, verification, simulation on Simulink. And then next step, we use HDL coder to generate RTL code automatically. And we need to use two kind of interface. The one is XE Lite for register access, and the other is XE Stream for video application. And then we use Vivado IP packager and IP integrator to pack those RTL codes as an IP block and integrate into any Zynq block design. So if you don't know what I'm talking about, please see my other video for detail. So we use two FPGA prototyping board for this application, the first one is Zboard, and with the FNC daughter card, and this daughter card has HDMI input and output. So the system overview would be look like this. The notebook will has HDMI output and output to Zynq to Zboard, and Zboard will do a Sobel filter and then output the result on the screen. And the application we run on ZC702 is slightly different, and input instead we use camera Vita 2000, so we can have live image input from camera and show the result on HDMI monitor. Those modules could be found on Avnet website, and here just look for your reference. The resolution is very high, and you can go to the website and check for more detail. So where to start? Maybe you will think this design must be very difficult, very complex. But actually, Avnet has been doing a great job on providing those reference design for us. We can build our system from here. So it's a very good start point. So you go to the website, and maybe you have to log in and download the FNC Imagine blah 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 tutorial. And because this reference design is built on Vivado 2013.3, so my suggestion is you install this version to fit more with the reference design. Or if you use some version like 2014, it might not be able to work. So just install this version. And next step. As the picture shown here, if you download the reference design and unzip it, you will see the folder look like this. And if you go to the solutions folder, there will be several tickles, and we use these two tickles to create our Vivado project. And once you create your project, you will see block design like this, and this one is for Zboard. And you will have Zynq PS, you will have I2C here, and you will have HDMI input block. You can open this block and see the detail, and you will have the HDMI output. The interface here is XC stream. So the video stream comes from HDMI input, and do the image processing here, doing the resampler and YUV to RGB, blah blah blah. And here is XC stream, and also you have XC interconnect for a register interface. And this one is for ZC702. You can see it's pretty much the same. So let's go to the next step. Okay, so once we have our Zynq design ready, and the next step will be generate RTL code from Simulink. And this is the result of a code generation. So you just take a look here. We have three interfaces. One is XC for light for a register interface, and the register will look like this. And offset 100 will be if you write 1 to this register, you will enable the Sobel filter. And the other two interface is XC stream video in and XC4 stream video out. Okay, so we use IP packager and IPI to integrate Sobel into Zynq design. So, as I mentioned, you will have to create these three XC interface as shown here. One is exit line, and the other two is exit string, slave, and master. So the final Zynq design will look like this. This is on Z-board. So on the output of HDMI block here, and the SC4 string, the data will come from here to our Sobel filter, and our Sobel filter will do the Sobel algorithm and bring the output to the HDMI output block. Pretty straightforward. And the ZC702 is pretty much the same. We just add a new block in between the original design to do the extra video image processing. So the final step will be create SDK project and test it. So the documentation in the reference design is very comprehensive, so you can just follow the PDF. But we need to add one new code to enable Sobel filter. So pretty easy. Just you can write something like this, and offset you can change to your own offset. And this is something we should notice. If we choose clock for our design for Sobel filter, it's up run at 150 megahertz. So according to the document, if we run at least 148.5 megahertz, we can have full HD frame rate, 60 frame per second performance on the FPGA platform. Okay, so actually I pre-recorded 2 videos for these 2 demos, but before I play the demo, let's look at the utilization report, which is many of my coworker or many of you might be wondering what is the differences between high-level synthesis from Xilinx and HDL Coder from Mathworks. Alright, so I put the utilization report here so you can have a quick comparison about these 2 tools. And I have the data from for high-level synthesis from the document from this XAPP890, and this is using high-level synthesis tool to convert C to RTL, actually C to FPGA. So here's the result. Overall, it's obviously HDL Coder is better. HDL Coder use less resource than a high-level synthesis. So they are doing the same task, Sobel filter. Of course, you can perhaps you can further optimize the options in high-level synthesis to try to get better result. Just so you know, I didn't do any optimization on the HDL Coder as well. So just raw data, I just put it here for your comparison. But despite the output, the resource HDL code used is less than high-level synthesis, and the price might be another issue if you try to purchase these tools. And as far as I know, HDL Coder is more expensive than high-level synthesis, so it's up to you to either use high-level synthesis but might suffer more resources, or use HDL Coder for a better result, but it costs you a little more. Okay, let's play the pre-recorded video for your reference. Thank you.